Hello, all. Today's lecture is about the Drude model. Drude model for the conductivity of electrons in a metal. So, what is a metal? Metal is a state of a material that has free electron gas. Free electron gas. This is an important concept. Free electron. What is assumed that there is a metal which has ionic core in it, and there is a electron which is free to move like a gas in a material. So let's draw a picture. So this is a typical solid which has a ionic core in it of which are fixed in the position, and around it is the sea of electrons which are roaming freely across the solid. Free electron. This free electron is called that as a free electron gas. It behaves similarly as a ideal gas. For this, we have made two assumptions. First assumption is that collision between two electrons are instantaneous. Means means the two electrons are coming. They just simply come and scatter and go in a different direction. And between the one scattering and the next scattering, there is no interaction between two electrons, and these electrons are also not interacting with ionic cores. So it means collision is instantaneous, and between one collision to another collision there is no interaction between them. And second is that the mean time between these two collision is independent of electron position and velocity. Mean time between collision is position and velocity of an electron. Now let us explain this concept further with the help of a 3D model. Let's draw a cube first. So this is a cube of a length L, and let's also draw its coordinate X, Y, and Z. And it has a electron moving towards the right with the velocity Vx, right? The momentum of this electron will be mass into multiplied by velocity, right? Now this is going in towards the right, but when it reaches the surface, it just simply reflects back. So it just simply changes direction. Now it is minus Vx. So change in momentum will be final momentum, which is minus mvx, minus initial momentum, which is also mvx. So overall change in momentum is minus 2 mvx. From the law of conversion of momentum, so the momentum transferred will be momentum transferred to the surface will be 2 mvx, right? Now we know that, so the momentum transferred to the surface is 2 mvx. Now interesting thing is to be noticed is that when electron reaches the surface, it will be reflected back, and from that surface it will again reflect, so it will come back to this surface after traveling 2L of distance. So, so the time so the time between these two collision at the surface, time between two collision to the surface will be distance that it has traveled, which is 2L, on velocity is Vx, right? Now moving forward, we know that force is change in momentum with respect to time, and we know, so the force, the change in momentum that was transferred to wall was 2 mvx, and the time to was to be 12 by vx. So it will be mvx square by L. Now this force, this is the force that an electron will exert at the surface, and this force will be one for one particle, right? One. Now similarly there will be multiple particle and particles. So the overall force by the combining all the on the electron particles will be summation of mvx1 square upon L plus mvx2 square upon L plus mvx square upon L3, and similarly. So this can be written as summation mvx I square upon L, where I equal to 1 to n, right? Now, what will be the total number of electron in it, or total number of electron particles? Here, the electron are assumed as a particle, like ideal gas. It will be number of moles multiply with Avogadro number, right? Now, this summation terms can be written in that case. That written as can be written as, since we also now know the total number of particles, so it will be mass multiplied with mole and Avogadro number and L will come out, and the velocity will be now square mean of average square velocity, right? This will be the force that is being exerted on the surface. Now this was the case for 1D, right? This equation was for 1D. Now for 3D, what it will be, the velocity will be v square is x component plus y component plus z component, right? Now if we assume that this material is same towards in all three directions, they are same. So it can be written as velocity, every velocity in 3D case will be 3 times of Vx square, right? Or Vx square will be V square by 3, right? In that case, that total force that is being exerted on the surface will be m n, that will number, average velocity square, average velocity upon 3L, right? So this is the total force. Right? Now we have force. Let's calculate the pressure. We know that pressure is force per unit area, right? So the pressure that will be exerted will be the force which we calculated F. Area will be, length was L, so area will be L square. So it will be M N N A V square by L cube, right? Now interestingly, this is L cube. So this is also the volume of the cube, right? So the pressure will be M N N A upon 3 into volume, right? If I take volume towards the left, so it will become PV equal to M N N A square by 3, right? So, and we know from the ideal gas law that PV equal to nRT, right? So let's put this in this equation. So it will become nRT equal to M N N A square by 3. Can will cancel out n. So it will be RT equal to M N A P square by 3. Right? Or we can also write this equation as, we can write also this equation as M V square will be equal to 3 RT upon Na, right? Now we know the our this mv square, which is close to kinetic energy, if we divide it by 2 on both sides, so it will become, this will become kinetic energy 3 by 2 RT by Na, right? This is the kinetic energy. Now we also know that Boltzmann constant is R, which is gas constant, upon Avogadro number. Therefore, the kinetic energy is P by 2 Boltzmann constant KT. This is kinetic energy of an electron in a cube, in a metallic cube, right? Now, if there are total of anti-electron in the materials, so total energy E will be 3 by 2 anti KBT, right? Now let's specific volume heat capacity. Was kept as PV is total energy upon temperature, right? So it will be differentiation of the temperature 3 by 2 and T kb. Now if I summarize overall, that we start with what we did. We start with the explanation of the Drude model. What it has, there is a metal which has a positive ionic core, and the electrons are moving freely inside these cubes. Right, they are moving freely inside the cubes, so they are assumed as a free electron gases. Here we assume that electrons are not interacting with the ions, so they are free to move, and they are behaving like the ideal gas. So where we assume that the collision that is happening between electron are instantaneous. So and between one collision to another collision, there is no interaction between them. And second assumption was the mean time between the collision is independent of the velocity and the position. To start with, we assume that we have a cube and there is a one single electron which moving towards the right in x direction with the velocity vx. So the its momentum will be mvx. So the change, therefore, when it is reflected back, the change of momentum will be minus 2 mvx. The momentum that is transferred to the surface will be because of the conversion of conservation of momentum will be 2 mvx, and and the and when the electron reach this surface towards the right, the second time it will reach, it has to travel the distance of 2l. So the time between the two collision to the surface will be 2vl by vx. Therefore, we calculated the force, which will be change in momentum with respect to time. So when we put this equation, we get mvx uh, square upon L. This is for the one electron. Now there are multiple electrons. Let's say there are n electrons. So we do the summation of those electrons, and right, and we know that the total particle will be inside a cube is number of mole and multiply with the Avogadro number. So this summation can be removed and written as F equal to mv na vx square by L. This is the case for the 1D. Right? For the 3D case, we have to we have to consider all three directions. So it will be vx square, vy square plus vz square. Since it is isotropic, they are same in all three directions. So it can be written 3vx. So vx will be v square by 3. So with this, in this way we get the total force. Now we know the pressure that will be put on the surface will be force by area. So force will be so pressure will be force upon area is L square. Now there is was already an L. There was already L, so it become the L cube. So it become the volume. So when we take it to this, we get the PV and this expression. So we know from the ideal gas PV equal to nRT. So when we put we get RT equal to M in this expression. When we arrange it, so when we arrange it such that uh, such that that we get the 1 by 2 mv square, which is kinetic energy, which is 3 by 2 RT by Na, and we know the work constant is defined by R by Na, so we get the expression of kinetic energy, which is 3 by 2 kBT. Total energy will be total number of particles, let's say is NT, 3 by 2 NT kBT. Now the specific volume heat capacity, which is defined as the differentiation of total energy with respect to time at constant volume. So we will get 3 by 2 K 3 by 2 NT kB. This expression will be used in the future. Thank you for your time.